Now we're going to talk about electric fields. So far in physics, we've talked about forces as something that applies to an object caused by an agent, where both the object and the agent are material bodies with mass. They're actual things. But the context that we're going to start studying now is forces that are caused by a field acting on an object. And a field is kind of an abstract idea. A field is, you can think of as something that fills up space. It's sort of an alteration of space. A field is still caused by something, but we're not really worried about what is causing it anymore. We're just worried about that field instead. And so you can think of a field as a bunch of individual vectors just floating in space, and what those represent is the force that an object would feel if they were at those different points. So, first of all, I know that when we use the word force field, there's a very specific image that comes to mind from science fiction of, a shimmering blue thing that bullets bounce off of. And that's not really what we're talking about. It's, like what I said, a vector at every point in space where something is experiencing a force if it's at that point in space. So let's look at a couple of examples. So if we have the ground and we're thinking of a bunch of different points that an object could be relative to the ground, that object is going to experience gravity pointing straight down, and the amount of gravity that it feels is going to be exactly the same no matter where it is, right? If it's a foot off the ground, if it's 3 feet off the ground, no matter where it is, it's going to feel the same amount of gravity. So if it's, a 1 kilogram object, it's going to feel 9.8 newtons worth of gravity. If we have an object floating around the Earth, so here is the Earth, the amount of gravity that something feels is going to be closer. It's going to be larger if it's close to the Earth. It's going to be weaker if it's far away, and it's always going to be pointing towards the Earth. So here's something large, here's something small, and we can just keep on doing that all the way around the Earth. I'm not doing a great job at keeping these the same as I go around the Earth, but close enough. Something kind of sort of like that. And then we have this science fiction idea of a force field where there's this shimmering shield. And if you hit that shimmering shield, it bounces way off. But there's not really any force anywhere else in space, just when you're right at that shield. So in each of these cases, we can talk about what the force is for a specific object. So this is, like I said, this 1 kilogram object at each of these points. And so this magnitude of this vector is 9.80 newtons. This is very specific. If we wanted to draw this again for a 2 kilogram object, we would have to draw a different set of vectors, right? All of these would be twice as long if we had this 2 kilogram object that we had at each one of these points. And we don't really want to do that, right? So instead, it would be great if we could draw a very related field that we had a weight or gravity per kilogram, right? And it would look almost exactly like this. We'd still have these arrows pointing straight down at every point, like that, but the magnitudes of these arrows would be 9.80 newtons per kilogram. So now it doesn't matter if you have a 1 or 2 kilogram object that you put around here. The length of these arrows are the same, and you can figure out the total amount of gravity or weight that that object experiences by multiplying the strength of this field times the mass of that that object that you're putting in there. So we called this a gravitational field strength. And it's, how much force per object mass that we insert into the force field.